For lesson 7.3, we're going to be proving trig identities. And really, we're streamlining this lesson in this video. Just want to call your attention to the very top of this page here. You can see we're reviewing the even functions. Cosine and secant are the even functions, so that if you ever had the cosine of negative theta, that's equivalent to the cosine of theta. Odd functions. Well, the rest of the trig functions are odd. The sine of negative theta would equal the negative sine of theta, and so forth for these three remaining functions as well. We have our basic definitions of our trig functions, such that tangent is sine over cosine, secant is 1 over cosine, and so forth. We have cofunction identities. That the cosine of 90 degrees minus theta, or pi over 2 radians minus theta, would be equal to the sine of theta. Likewise, the sine of pi over 2 minus theta would be the cosine of theta as well. This is all review. The Pythagorean identities right over here in this box where everything has been highlighted. Normally in a lesson, I would go through an exhaustive proof showing how this can be achieved. And you can see the notes off to the far right side here, just developing from the unit circle with an xy coordinate. It will lead you to be able to say that sine squared plus cosine squared is 1. This is something we've already used extensively. Likewise, cosine squared is equal to 1 minus sine squared. Sine squared is equal to 1 minus cosine squared. In green here are two other Pythagorean identities. Tangent squared plus 1 is secant squared, and 1 plus cotangent squared is cosecant squared. These are all tools that we're going to be using in this lesson. We're going to have to really have quite a few resources. We also have some very helpful algebra. Remember, if I gave you a quantity squared, a plus b squared, that'd be a squared plus 2ab plus b squared. Likewise, if I gave you a difference, a minus b squared, that we could FOIL out, multiply out, and get a squared minus 2ab plus b squared. And finally, a squared minus b squared is simply a plus b times a minus b. Well, we have all of this information in front of us. What are we really doing today? Well, we are going to transform expressions into other ones. We're going to show that one side of an equation could be transformed into the other side. To get us started, simplify tangent of x times the cosecant of x. Tangent, if you looked at the top page of the notes, would simply be sine over cosine. Cosecant is simply 1 over sine. And you can very quickly notice that the signs are going to cancel. You'd be left with 1 over the cosine of x. However, this is actually more simply written is the secant of x. Now, in all truth, most of the time you're going to prove identities. You'll be given, like for number 2, cosine of x raised up to the 4th minus sine of x raised to the 4th. Show that that's equivalent to cosine squared x minus sine squared of x. Please make sure you're always doing the following. Draw a bar down from the equal sign and work on just one side. In fact, what we're going to do is generally work on the more complicated side and try to show that this side can be transformed into the other. If I gave you cosine to the 4th of x minus sine to the 4th of x, very similarly, if I gave you a to the 4th minus b to the 4th, that's a difference of squares. That could factor into a squared plus b squared times a squared minus b squared. Why do I point that out? Well, we can certainly do that now. We can say this is cosine squared of x plus sine squared of x times cosine squared of x minus sine squared of x. And I do want to state something so very, very important. We must be looking at this other side. This we know is going to be our final answer. This is our destination. We know we're done when we can take this left-hand side and make it look like the right. I do want to just point out that the most famous of these Pythagorean identities is sine squared plus cosine squared is equal to 1. That's definitely the case right here. We'd get 1 on the left-hand side times cosine squared of x minus sine squared of x. Constantly looking off into this other side, we know this is our destination, and this is our ending point right here. We are now done. You'll see many teachers write QED, which is Latin for quod erat demonstratum, which is really saying what has been asked for has been demonstrated. And that means we have accomplished our proof. Let's take a look at number 3. Number 3 is a very, very famous identity, the type of which will require us to get a common denominator. Look at your two denominators. I hope we could quickly agree that we're going to need sine of x and also 1 plus the cosine of x. And fractions, of course, are definitely more complicated, so we are going to be working here trying to get a common denominator. I look at my first fraction, and very quickly we can see that we are missing a 1 plus cosine of x. So I'm going to multiply the denominator and the numerator by 1 plus the cosine of x. When I come over here to this sine of x all over 1 plus the cosine of x, we're quickly going to notice that we are missing the sine of x so that we could have our common denominator. Now, the common denominator effectively means we can now write those two fractions as 1 with this common denominator. Off to the left here, 1 plus cosine times 1 plus cosine. Well, I hope it's pretty obvious that this is really like a plus b quantity squared. 1 plus cosine times itself. So I hope we can quickly come to an agreement that this is 1 plus the cosine of x plus cosine squared x. It's effectively a squared plus 2ab plus b squared. Similarly, sine times sine would be sine squared of x. And at first glance, this might look like we've done more harm than good. You might think, oh my word, where do we go next? Well, again, I guess what I'm always trying to point out is our ultimate goal is to reach this 2 cosecant of x. But of course, as we're looking here, we can notice that cosine squared plus sine squared is that very famous identity that we just used a moment ago. That all collapses to just a 1. So things are looking a little bit better. Things have cleaned up just a little bit. And at this point, maybe we could even say, well, over here we'd have 2 plus 2 cosine of x all over sine of x times 1 plus the cosine of x. Well, from here, I hope you can notice that we could factor out a 2. And by the way, just looking back up to the very original problem, we know that in the end, we want to have 2 cosecant of x, which is really 2 over the sine of x. Look at this. The 1 plus cosine of x is cancel out. We're left with 2 cosecant of x, which is exactly where we needed to go. This is a very famous type of an identity where you need to multiply by missing pieces of a least common denominator. But again, good things are going to happen. Take a look at number 4. In general, please, please, please start on the more complicated side. And I hope right now you're looking at this thinking, well, wow, I don't see obvious algebra to do. I don't have a common denominator. But if we were to refer back to the Pythagorean identities, look at what we've highlighted in green. Secant squared is really tangent squared plus 1. Maybe, just maybe, that could come to our rescue. We could say, well, look, here's tangent squared of theta plus 1, and here's minus a tangent squared of theta. And I hope you'll notice very quickly that your tangent and negative tangent squared are going to cancel out. And then, very quickly, I hope you're going to notice that cotangent squared plus 1, or 1 plus cotangent squared, is also an identity. And we will quickly arrive at cosecant squared of theta. Okay, let's take a look at another. As we are looking at, say, number 5, I do want to make a quick comment about a very popular approach that we can have when we have a fraction, namely secant of theta all over 1 plus the cosine of theta. Generally, many students have disliked fractions in the past, namely because they do have their complications. And in this regard, we can consider this fraction to be a little more complicated. I'm going to multiply by the conjugate of the denominator. Remember something special about conjugates. I'm going to write to the far left side. If I give you a plus b times a minus b, that will multiply into a squared minus b squared. Why would that perhaps help us out? Well, down below we'll have 1 minus cosine squared of theta. A plus b times a minus b is a squared minus b squared. And then we could even begin to distribute this secant all the way through if you'd like. But why would this even be something that we'd like to approach? Well, squares will allow us to use Pythagorean identities. 1 minus cosine squared is sine squared. And then secant times cosine. Well, secant times cosine, my goodness, they're reciprocal functions. Secant times cosine is going to multiply simply to a 1. So that can help us out tremendously. From here, looking where we're going, you can say, well, I need to have a secant minus 1. I do have that. Maybe you'd like to just isolate this and say 1 over sine squared multiplied to secant theta minus 1 is the equivalent of dividing by sine squared. But 1 over sine squared is really cosecant squared of theta. And here we are. We would then be done. Okay, last one of this sort for number 6. Looking at that left-hand side, I think it's clear that the left-hand side is more complicated. But there is an identity, 1 plus tangent squared. Thank goodness is actually secant squared. And secant squared over secant just becomes secant. You can see now we're on our right-hand side. And we're good to go. So for homework, we're actually going to be looking at 19 through 63, every other odd, on page 474, 475.